Okay, with that, I'll switch over to Stavros. Ready to go?
Thank you very much, Ken. My name is Stavros Vougioukas, and I'm going to talk about agrobotics and harvesting, in particular, some of the research we are doing at UC Davis. UC Davis has a lot of faculty working on agrobotics, AI, and data applications. There is a smart farm initiative which is unfolding, and some pretty interesting news will come up very soon on a big initiative on AI. But I will focus today on harvesting, and this is something you already know. Most fresh market crops are hand harvested, and people are asking, who are outside of the field are asking, we've been to the moon, why is this so difficult? And the truth is that robotic harvesting is not that difficult. I mean, it has been showcased since 1985, but harvesting cost effectively is very, very hard. And if we were to look at the two main factors that influence the cost of harvesting, one is the picking efficiency. This is the percentage of the marketable fruits on the tree, let's say, that your machine or your picker can pick and pick safely in a way that are marketable. Now, picking efficiency is a percentage. A human picker achieves at least 95%, if not more. Now, we need to realize that out of the fruits on a tree, only a certain percentage are visible, and then only a certain percentage of the visible ones can be recognized by the either human picker or by the robot picker. A percent of them can be reached, another percentage can be safely detached, and another percentage can be safely conveyed to a bin. Now, unfortunately, all of those are multiplied together in order to give us the final percentage, your true picking efficiency. And if you think that...
Stavros, just one quick question. Are you using slides, by the way?
Yes.
We're not seeing them.
Oh, I am very sorry for that.
Ah, there we go.
I am terribly sorry. I was explaining that we need to multiply these percentages to get the final efficiency. Imagine multiplying 95%, which is a pretty good number, to the power of 5. That's only 77% efficiency. So you see how difficult it can get. And each of these factors depends on biology and horticulture, but also on engineering. The other very important factor is the picking throughput. How many seconds does it take to pick a fruit, or the inverse? And let me give you an example. A human picker on an orchard platform takes about 1.5 seconds to pick one apple and put it into the bag. A strawberry picker will take about 0.7 seconds to pick a single strawberry and pack it. These are pretty fast speeds. And again, if you want to calculate the time it takes to get a fruit, you need to take the time needed to perceive that the fruit is there, the time needed to reach it, detach it successfully, and convey it. And you need to add all those times to get your picking throughput. So you see that all of these factors need to be taken into consideration, and they're also conflicting. If you want a very high percentage of efficiency, you may need to go slower. So I have the highest respect for all the people out there who are building real machines, hopefully commercial machines that will achieve this task. What I'm doing in my lab to a large extent is I'm looking into robotic harvest aids. These are machines that increase worker efficiency. So we are not replacing people, we just utilize their work better. We generate data with those machines, and we explore worker and robot interactions. This is an example. It shows you a strawberry field where people are rushing out to deliver full trays and get empty trays. They spend 10 to 20% of their time just walking. So this is one project that we had. We built a team of totally autonomous robots that are doing the logistics for them. You can think of them as Amazon robots in the field. They coordinate, they go to the picker, they get the tray and take it back. How is this achieved? Well, this is a person picking strawberries. We built a special carrito, a picking device with GPS, load cells. We are measuring the weight and position of the fruit. We are sending it in real time to the robot fleet. The robots get deployed, and we achieve 10 to 20% increase in efficiency, and we generate yield maps. Another example of a similar situation is fruit harvesting, where people go on tall ladders. There are orchard platforms that people work on in order to pick without ladders. The problem is that most of those platforms are static in the sense that the pickers pick from fixed heights. That means that they do zone harvesting. They harvest at different zones. And the problem with that is that the fruit distribution differs and the picking speed differs. So there's an imbalance of labor supply and labor demand. So our project was about finding all the fruit distributions in front of a platform and making a platform that will result in variable zone harvesting. So you try to match in real time picking speed with fruit balance, fruit load. This is the platform that we built. This is in collaboration with Carnegie Mellon. And this is a video of the platform moving into the orchard. This is the camera system. It's detecting all the fruits or the ones that are visible. It creates a fruit distribution heat map. It sends that to the platform. The platform also monitors how fast people are picking. And you can see here that the platform elevates on its own. This is robotic, where the pickers are. It also controls the speed of the platform, and we increase the efficiency by up to 25%. So these are just some examples of harvest aid machines. We are now working on another project where we are attacking the issue of high throughput. Our approach is to use a larger number of simpler arms, but the trick here is that if you have multiple arms, then you need to really do some intelligent scheduling in order to do fruit assignment. And also we are working on perception from multiple viewpoints and active leaf agitation for better visibility. So with that, I would like to conclude, and I'll be happy to discuss further about this research.
Excellent. Thank you, Stavros. We really appreciate that. Beautiful. So let's see, I will give the floor to Stefano if you have a question for him, and then we'll switch over to Josh.
Yes, I have a question. So I've been following Stavros' work since a while, and what I like is that the final feature is always human-centric. In a sense, these are always machines for assisting humans and being more efficient and help them out. So I was wondering if you have, maybe even anecdotally, what is the acceptance of the pickers when they are using these machines? What are the reactions? Because we can think about all of this in a lab, and then we build them to the field, and maybe there is a completely unexpected interaction with the end user. So I was wondering if you have anything you can share.
That's a very interesting question. It depends really on the machine. First of all, if they feel that the machine will replace them, they hate it, which makes sense. On the case of the orchard platform, they really loved it because it made it easier for them to pick without kneeling or stretching too much, because the computer was doing that for them. And it also increased their picking speed, so they made more money. In the case of the strawberry harvest aids, they kind of like the robots. Initially, they didn't like the picking carts because whatever is different or makes them perhaps pick a little bit slower, or they feel it's going to make them pick slowly, then they don't accept it that easily. You need to really talk to them, discuss, iterate, and make sure that they are part of the loop. I mean, otherwise you can't even perform experiments if they refuse to collaborate. So I think the answer would be they're not extremely open, but once they see the benefit, they embrace it.
Thanks.
Thank you, Stavros, and actually Stefano for bringing that up, because there's also this incredible story which I only learned about recently, about how the tomatoes that were developed and the harvesting system that was developed in the, what was it, the 80s?
60s.
Where it was the 60s. Okay, great. And that was it. And it was an automated system. And so it looked extremely efficient and valuable, but it backfired enormously. And it's a really cautionary tale, I think, for all of us. Stavros, if you have a link or anything to the to that story, you could put in the chat. That might be helpful.
I will do
because
sure.
when I heard about it, it was very extremely eye-opening about I would say, the social political pressures around this kind of work.